Hi, my name is Sam Witte. I am a postdoc at the Grappa Institute in the University of Amsterdam. This is my presentation for the workshop on weak interactions and neutrinos. I'm going to be talking today about work that I've done in collaboration with Dion Nordhaus, Tom Edwards, and Christoph Venegar on axion-photon conversion in the magnetospheres of neutron stars. So let me start with a brief introduction to the axion, which means a brief introduction to the so-called strong CP problem. The problem, sort of simply put, can be phrased in the following manner. We have a CP violating term in the center model Lagrangian, QCD Lagrangian. This is the so-called theta term, and it's directly proportional to this parameter theta bar. The overall size of the theta term, or the theta bar parameter, directly controls the size of the neutron electric dipole moment. Various groups have tried to measure the neutron electric dipole moment and have placed constraints on the size of that theta bar parameter at the level of about 5 times 10 to the minus 11. So the strong CP problem is a fine-tuning problem of why theta bar is so small, or equivalently, why CP is so well conserved in QCD. The most preferred solution that dates back to the 1970s was proposed by Roberto Bachet and Helen Quinn, is to promote this theta bar term to some dynamical quantity and allow that dynamical quantity to relax the theta bar term to a CP conserving vacuum. So they do this by introducing a new U1 global symmetry. The pseudo-Goldstone boson of that symmetry is the axion, this particle A here. It's going to couple to the GG dual field strength tensor in the same way that theta bar did. And at high temperatures, it's going to have the conventional wine bottle potential, but non-perturbative effects in QCD are going to generate a tilt of that potential such that the CP conserving vacuum is favored. Now we can ask the question, given that this is such a nice solution to the strong CP problem, can this also solve other problems in physics? In particular here, we're going to ask whether it can solve the problem of dark matter. Now, what you do if you look at the lifetime is you can find out that the axion will become cosmologically stable if its mass is sufficiently light, in particular if it's less than about 10 or so eV. We can actually impose stronger constraints, though, if we require it to account for the entirety of dark matter. So if we ask, what are the conditions in order to produce sufficient abundance of cold relic axions in the early universe, we can place additional sort of constraints on the mass, saying that the mass should be, roughly speaking, larger than about 10 to the minus 6 eV in order to avoid overproduction of axions, and less than about 10 to the minus 3 eV in order to evade astrophysical constraints. So this is sort of the sweet spot in which the QCD axion can also account for dark matter. Now, how do we detect axions? One of the easiest ways is to try and exploit the coupling of the axion to electromagnetism. In particular, it couples in the following way via a E dot B like term. So if we take a sort of static background magnetic field, this implies that the axion can directly convert into a photon or vice versa. Now, the probability of this conversion is going to be proportional to the coupling squared and the magnetic field squared. And by dimensional analysis, you can convince yourself that we're missing a factor of length scale squared. And the question is, what is that length scale that's setting this conversion probability? In the non-adiabatic limit, this length scale is going to be set by the effective length over which the axion and photon can coherently oscillate. If I go to a vacuum and I have a non-relativistic axion, the momentum mismatch between the axion and the photon will be large, meaning that they will not coherently oscillate. And as such, my length scale will be set by the smallest scale in the game, the de Broglie wavelength of the axion. In the limit, however, where I can generate an effective photon mass, so if I go to dilute plasma, for example, if I can match that photon mass to the axion mass, I can allow these particles to oscillate coherently over many, many periods. And in doing so, I can dramatically increase my axion-photon conversion probability. So when we talk about ideal targets or ideal environments to look for axion-photon conversion, we really want places where we have large magnetic fields and dilute plasmas. Well, when you think about large magnetic fields, the obvious place to look is neutron stars. These have enormous magnetic dipole configurations with magnetic field strengths at the surface reaching 10 to the 14, 10 to the 15 Gauss. What's nice on top of that is that if you have this large magnetic field around a neutron star that's rotating in a vacuum, that will generate an electric field that will rip charges off the surface of the neutron star. Those charges will then redistribute themselves in order to cancel the induced electric field. And in doing so, you're going to generate a dilute plasma in the magnetosphere. Because the magnetic field is radially falling off, the plasma distribution will also be radially falling off. But because of the structure of the magnetic field, you're also going to have a structure to the plasma distribution. And that's what I'm showing here in these sort of gray contours. This is an isocontour of electron number density, or equivalently an isocontour of effective photon mass. And what you see here are the structures, the sort of three structures. You have a torus-like feature sitting here in the center. This is being defined by the closed magnetic field lines. You have two lobe-like features on the top and the bottom, and these are being aligned with the open magnetic field lines. And between the sort of torus and the domes, what you find are these throats, which sort of dive in towards the neutron star, characterized by extremely low plasma density. Now, the idea that's been proposed for many years, but really pushed in the last, say, 3 or so years, is that we can look for axions that are falling in axions will fall into the neutron star, into the magnetosphere. Occasionally, some of these axions will cross that resonant region where the axion mass matches the photon mass, the effective photon mass. This will enhance the conversion probability into photons. These photons will leave the magnetosphere, and then we can look for some flux, some narrow spectral feature of photons coming from neutron stars. And in particular, we're going to find that the energy of those photons should be, roughly speaking, aligned with the mass of the axion. And because the mass of the axion is sitting in this 10 to the minus 6 to 10 to the minus 3 eV range, we expect this line to be situated in the radio photon band. Now, this is a really nice idea, and there's a lot of promise that this might give us access to the QCD axion bands, sort of the conventional parameter space of the QCD axion. But there's a large list of uncertainties which are still open in this problem that we really need to sort out in order to robustly assess and understand what the expected radio signal will be. And I think you can sort of categorize these in three different regimes. You have sort of large-scale astrophysics questions, small-scale astrophysics questions, and questions associated with plasma and particle physics. In the context of sort of the large-scale astrophysics, we have questions about the dark matter phase space. You know, what is the halo profile? What is the substructure of dark matter? Do we have axion mini clusters? We also have macroscopic questions associated with the neutron star populations. You know, how are these distributed in the galaxy? What is the distribution of magnetic fields and misalignment angles and rotational frequencies of the neutron star populations in the galactic center? On the smaller scales, we have questions about the magnetosphere. We need to understand the distribution of plasma, for example. Do we have plasma homogeneities? Do we have relativistic plasmas near the neutron star? Do we have non-poloidal B fields? All of these can influence the characteristic distribution of the conversion surface and the propagation of photons. And then finally, in this sort of this fourth category, we have what I'm going to call from photon production to detection, which is, you know, how do axions and photons mix in a three-dimensional and homogeneous plasma? How do photons undergo refraction and reflection and absorption as they exit those magnetospheres? And really, what is that radio signature we're looking for? You know, is it a line? Is it a broadened line? Do we have time dependence of that signal? Can we identify how sensitive we are to our viewing angle? And there's a large list of questions that we really need to understand in order to robustly search for these signatures. So in this talk, I'm really only going to focus on this fourth category. This is really what we have been focusing on as a group. And so I will adopt relatively simplistic assumptions for these remaining categories, in particular, assuming, you know, a simple NFW profile for the dark matter distribution. I will focus on observations of a particular magnetar that's sitting in the galactic center, whose properties have been relatively well characterized. And I will adopt the Goldreich-Julian magnetosphere model. And the questions we want to ask are, how accurate is the current formalism? Does this amount to an uncertainty of a factor of 5 or 10 to the 5 in the flux? And can we identify meaningful ways to actually search for these things once we've started to account for all of these different effects? So before I discuss some of the assumptions that have been made and how our formalism can correct upon them, I want to discuss the overview of our formalism because it is really an end-to-end process that characterizes the entirety of the axion signal or photon signal from the point of conversion to the point of detection. So I'm going to run this animation here on the left and describe what is actually happening. So our procedure starts with a Monte Carlo integration of the axion phase space at the conversion surface near the neutron star. This allows us to essentially seed individual photons with a fixed momentum and a fixed energy, and allows us to reweight these photons or give each photon a weight associated with the overall dark matter phase space, which would have sourced that individual photon. Once we have that individual momentum and the location and the momentum direction of that photon, we can use that to compute the conversion probability of each individual photon and reweight each photon by that factor. We then have developed an auto-differentiable ray tracing algorithm that allows us to propagate photons through the plasma homogeneities to asymptotic infinity. This allows us to account for both refraction of photons and reflection of photons. And if you look closely at the photons that are coming out of this magnetosphere on the left-hand plot here, what you'll find is that you can physically see these reflections and refractions of the photons near the conversion surface. At larger distances, the dispersion relation becomes the free space dispersion relation, and photons travel in straight lines and are unimpeded. But very close to the surface, all of these effects play a very important role. Now, during this ray tracing process, we can also account for energy exchanges between the photon and the plasma, meaning we can account for whether or not there's line broadening of the plasma of the spectral line due to interactions with the plasma. Finally, once we've propagated these photons to large distances, we can take their trajectories. We can compute the optical depth of each individual trajectory, and we can also go and look whether or not there was any additional axion-photon dephasing near the conversion surface, which is something I'll discuss in more detail in 1 second. So once we've done all of this, this allows us to generate sky maps that characterize the signal. This will be able to characterize, for example, the flux over the entire sky. We'll be able to characterize the center of the line over the entire sky, the characteristic width over the entire sky. And that means we can actually start to make robust predictions for both individual neutron stars and populations of neutron stars. So if we do this process, what we find are something like this. So this left-hand sky map is plotting the fractional flux, or the fractional rate at which photons are crossing a spherical surface at asymptotic infinity in units of log 10. And what I want to point out here is that you have these very, very two strong bands, these very, very narrow features that are crossing the sky. These correspond to the spatial regions in which you have those throats, those very characteristically low plasma densities. And what's happening is the refraction of photons is preferentially funneling photons into these low plasma density regions, these vacuum regions. And this is greatly enhancing the anisotropy of the signal, and by many orders of magnitude. In the right-hand plot, what I'm showing is the characteristic line width as a function of the sky relative to the axion mass. So this is again in log 10 units. If the line width were only characterized by the asymptotic axion distribution, you would expect this width to be on the order of, say, 10 to the minus 6 or so, corresponding to these very dark regions. What you find when you do this actual calculation is that the plasma interactions tend to induce line broadening over the entirety of the sky, or most of the sky. And in particular, in these high flux bands, you get an additional strengthening of the broadening due to the fact that refraction is extremely strong in these regions. So the energy that's imparted to or extracted from those of those photons induces particularly broad spectral features in the regions where you expect the largest flux, which means we really need to understand the trade-off between, for example, looking for narrow features in lower flux regions or looking for broadened regions in high flux regions. Now, there's been quite a few assumptions that have gone into the analytic formalism that has basically been used in every work until now. I don't want to get into all of them, but I want to just discuss them very, very briefly. And I want to get into the details of a few of them and show how our formalism can now correct for and actually start to make robust statements about the axion signal without having to resort to some of these approximations. So one assumption that's been made is that photon trajectories at the conversion surface are perfectly radial, and that the conversion surface itself is approximately radial. The secondary approximation is a geometric effect that's, amounts to an order 1 correction. But the first one, as I'll show you in a moment, does not. People have also been assuming that axion-photon conversion can be treated in 1 dimension. As you move to a 3-dimensional inhomogeneous plasma, this becomes far more difficult to treat. But I'll discuss how our formalism is allowing us to start to work in 2 dimensions and what that means for the overall flux of the axion signal. There's also been the assumption that the width of the radial line is set by the asymptotic axion velocity distribution, which, as I just showed you, is not true, as well as the fact that refraction does not play a major role in inducing anisotropy, another assumption which we have shown to not be true. And finally, there's been the assumption that radiophotons can exit the magnetosphere without being absorbed, and I'll discuss that briefly on another slide. So let's start with the fact that the assumption that was made that photon trajectories at the conversion surface are radial. I told you that the conversion probability is proportional to this coherence length squared. So if we start by considering a simple Axion-Photon conversion in one dimension, what we can do is write down the plane wave solutions in this one dimension with a varying plasma mass. And what you find is that when the plasma mass is roughly equivalent to the axion mass, these plane waves oscillate coherently in phase. However, as the plasma mass varies further and further away from that axion mass, you expect a decoherence of the axion and photon waveforms. And that it means that your conversion length is going to be, roughly speaking, inversely proportional to the square of the line of sight derivative of your photon momentum. So if my photon momentum changes a lot due to the fact that I have large plasma gradients, I expect to have a very, very small conversion length. Now, when you make the radial approximation, what that means is that I can actually write down an analytic derivative for this conversion length. And that's nice if we want to understand approximate formalisms and make rough estimations. But that radial approximation isn't necessarily true as you have a strongly inhomogeneous plasma with large plasma gradients. So what I can say is that we have gone through our formalism, generated millions of trajectories, and looked at the derivatives directly at the conversion surface of each photon and compared it to what you would have obtained with the radial approximation. And here's a histogram, both of the radial approximation in blue and of the true gradients in red. And what you find when you look, compare this, this line of sight derivative of the photon momentum, is again in log 10 units, is that there are order of magnitude discrepancies between this approximation and reality, meaning that we're going to have order of magnitude effects on the overall axion-photon flux. So this is an extremely important thing to account for. There was also the assumption that we can approximate the axion-photon mixing using a one-dimensional conversion probability. Let me show you how that looks. If you have, for example, an axion in this two-dimensional space, traversing along this blue line, and you have some sort of curved surface, this, where the plasma mass equals the axion mass, we can then assume, for example, in the one-dimensional formalism, that the photon travels along a one-dimensional straight line out. We can compute the gradient of the plasma at that point along that trajectory, and we can define this coherence length, this sort of red region. In reality, since photons undergo refraction, they're going to refract on small distances, and they may decohere from the axion on much smaller distances than the coherence length itself. And if that happens, you're going to induce a heavy suppression to the coherence length. So using our formalism, after we've obtained the trajectories, we can go ahead and recompute the phase overlap or the phase mismatch between the incoming axion or the line of sight photon that would have been obtained from the actual refracted photon, and we can retroactively correct for this conversion length suppression. And as with the previous case, this can also introduce order of magnitude effects in the conversion probability. We're working on a more rigorous two-dimensional conversion probability right now before going to 3 dimensions, which may or may not be possible, but this clearly has an enormous impact immediately on the conversion probability. So the final assumption I want to address is that radiophotons exit the magnetosphere without being absorbed. If you have a plasma in a background magnetic field, you're going to quantize the energy levels of the individual electrons into so-called Landau levels, where the characteristic energy splitting is set by the cyclotron spinning, that QB over ME term. In large magnetic fields and in cold plasmas, all of your electrons are going to be sitting in the lowest Landau level orbits. And so naively, you might say, well, why does this matter? This matters because the photons need to traverse from a region of large magnetic fields to small magnetic fields, meaning this energy spacing between the Landau levels is going to be shrinking. And in particular, there's going to be a range at which the photon energy that we've generated near the surface of the neutron star is going to cross that cyclotron frequency. And when that happens, these photons can be resonantly absorbed by the plasma. And so this resonant absorption process can induce a strong absorption feature into our radio signature. And what you find if you do this more carefully is that larger magnetic fields typically tend to lead to more absorption. So this is contrary to the initial statement I said is we want to look for the largest magnetic fields we can. Actually, that may not be true. And in particular, if you look, for example, at surface magnetic field strengths on the order of 5 times 10 to the 14 Gauss, we can compute the optical depth over the surface of the sky. And what you find is that you get order 1 factors of the optical depth. So you're starting to get exponential suppression of the radial flux around these magnetic field strengths for large regions of the sky. Okay, with all of that said, I want to summarize here in this final sort of projected sensitivity plot, which is projected using sort of SKA, so future radio telescopes. What we have here in green is the QCD axion band. This projection is made using a particular magnetar that's sitting near the galactic center and assuming an NFW profile. And I really only want to highlight a few different things in this plot. What I'd like to highlight first is this purple line, which is an approximate, sort of the approximate formula that you would expect had you not used our numerical formalism, but had you had adopted the sort of analytic formalism that has been used again until now. Using our numerical effects, including, for example, all of these corrections to the conversion length, including the anisotropy of the signal, you can characterize how sensitive you are to that viewing angle by plotting, for example, the limit you would derive, assuming you are sensitive to the minimum flux on the sky, or optimistically the maximum. And that minimum or maximum viewing angle sensitivity is characterized by these vertical bars, theta min and theta max, as a function of, again, the axion mass. If you were to marginalize over your viewing angle, you would get this thick black line, which is what we're calling fiducial, not because we believe that this is the best thing to do or the most meaningful thing to do, but because this is what has been adopted in various points in the literature to derive constraints on the Axion-Photon coupling. And if I compare these sort of black vertical bars or the black line to the characteristic purple line, you'll see that in many cases you are at least an order of magnitude, if not 2 orders of magnitude suppressed in the Axion-Photon coupling, meaning you are up to 4 orders of magnitude suppressed, for example, in the luminosity of the signal. So the effects we've discussed here have incredibly important impact on the overall flux of the radio signature. They also have an important aspect on determining the time dependence and determining the width of the signature. And so the next steps moving forward are to really identify optimal search strategies to look for radio photons, understand what type of targets are going to be most promising, understanding which type of targets are going to be most robust, and making sure that we can characterize the signal accurately enough to meaningfully constrain or look for axions. Before finishing, I just want to highlight that despite all of these suppressions, we seem to still have sensitivity to some parts of the QCD axion parameter space. So this method still seems to offer a lot of promise in the future, although we do need to make a lot of work on understanding the uncertainties associated with these plasma effects and associated with the magnetospheres if we want to be able to meaningfully constrain the axion. Thank you very much.